think it's good to start this subject in the same way as was done, as people historically in astronomy have done. So, well, let's first start with the subject itself. Why is this useful? I'm going to talk about stellar populations. And the word stellar populations has been used by all the previous speakers. Not very much. I was thinking that they might already talk about it quite a bit, but they've left the introduction to me. Stellar populations are extremely important because they contain fossil information about everything which has happened in the universe. Of course, this information, most of the information can never be retrieved, but quite a bit of it, we are in astronomy in a really nice position that we can retrieve quite a bit of it. And for example, with populations you can find out in principle how old the universe, or at least how old the oldest stellar populations in the universe are. We might understand more about how the atoms that we consist of, where they come from, what the future of our galaxy will be and the future of our atoms will be. And stellar populations really is the interface, a very important interface between cosmology and stellar astrophysics. So the field by itself is a very important field. But it's a complicated field. I'll show you. So I will start this series today and tomorrow in mainly with discussing the methodology that has been used in the field of stellar populations, especially in the field of stellar populations of nearby objects. And after that, I will discuss in the last two talks several results in early type galaxies, spiral galaxies, smaller systems, for example dwarfs, globular clusters and so on, and then briefly in galaxies at higher redshift. I mean, to deal with that well would have probably taken a lot more than just a part of a lecture. So the connection to the other lectures, well, there are connections to everyone because stellar populations are intimately connected to the ISM, the morphology, dynamics, star formation, potential, and so on, as for example was clear already from Daniela Calzetti's talk. So there will be lots and lots of connections. The first two talks, I guess there the connections will be less present than later, but you'll find out the methodology that I'm explaining here in the first two lectures probably also will be discussed by or talked or used by the other lecturers. So I'm also looking, like the others, I'm looking forward to an exciting winter school, and during the talk, after the talk, whatever, I'm also looking forward to your questions or comments or whatever. So, my first talk today, I will mainly talk about resolved stellar populations. Let's see how fast this goes. Maybe, if time allows it, also we'll start a little bit with the unresolved stellar populations. And I'll start, as I said, from the historical perspective. Which, in fact, this is also quite nice at this conference because also John Comedy and Ron Buter have talked about this as well. So, but this is, of course, not an old image. This is an image. This is, I think, a 144 orbit image taken with the ACS of the galaxy M51. This is a two-color image with the three bands. And let's go and zoom in on it. So near the cross, I zoom in and see several individual stars already. I can zoom in once more. And you can see a whole field of stars. This is M51. This is the galaxy at a distance of something like 8 megaparsecs, half the distance of the Virgo cluster. So what do we see? We see lots and lots of very bright, oops, go back. Lots and lots of, yeah, there it goes, of bright stars, which also from the ground are sometimes visible. Red and blue bright stars. So let's say red and blue. Well, we'll see later what they are. Probably the blue ones are large main sequence stars. The red ones are giants. And okay, now this doesn't work anymore. So, and this is a different area in the same galaxy. This is in between the arms. So you see, just by looking, that the populations are very different. The bright stars in the previous image are all gone. Both the bright ones and both the blue ones and the red ones. There are, however, still some of these stars which are individual stars which are still visible. Like, well, here, for example, in this area, here, this one, and so on. Clearly, populations are different. So, let's go a factor 10 closer. And then we get to the one of the companions of M31, the galaxy M33. And also there, I'm going to use the HST and see where we get. This is an area near a spiral arm. And you see, in fact, the same object. You see bright blue stars. And you also see redder objects. And here, zoom in more. Of course, out here, it's easier to get to resolve individual stars. This is close to, this is still local group. But there's a clear couple of clusters in this galaxy resolved easily into individual blue stars. But in the local group, we can go to other galaxies. So we can go to a galaxy which is called elliptical, dwarf elliptical, in fact, energy 205. And you see indeed from the integrated colors that it looks red. And we can then resolve this object into individual stars. And this is an area near the center. You see this dust patch here, which is this patch here. So we are really close to the center. But here we see basically everything. Bright blue stars, bright red stars, and so on. But very different from M33. The really big blue stars are not present. So now we go to the third galaxy, M32. So instead of this one down below, we go to the other dwarf elliptical companion, M32. And here we see this. I haven't gone to the center of the object on the left because there the confusion is so large that you won't see much. But here you see still a large number of stars. This is at the same resolution as the previous one. But you see here it's still redder than before. And but also here we see all kinds of individual stars. So this is basically the situation of Walter Bade in 1944 or before, where he used the Mount Wilson telescope, which at that time was, well, basically he was a staff astronomer at Mount Wilson. He had quite a few nights available on the telescope. They say the city of Los Angeles in the wartime was a bit darker than normal. I don't know how true that was. But he waited for specific nights with good seeing, so where the atmospheric conditions were good. And in these nights, he looked at M31, M32, and the companions, and basically saw two populations. One population, as he says, looking like globular clusters in our galaxy, and one population looking like the disk of our galaxy. Okay. Now, I'm going to put here now another galaxy, NGC 891, which some people say it's a twin of our galaxy, so it looks very similar to our object itself, our galaxy itself. This object also has been observed with the ACS. Remember, it's at 10 megaparsec, so a bit like M51. This is the area, one of the areas that has been observed, and now we're going to take an image near the red plus sign, and here it looks like this. So this looks very much, again, like what we saw in M32, reddish populations there. So this is so we have now found several kinds of populations. The population in M51 with bright blue stars, the population out here in M32 with more or less with reddish objects, not so bright, and then MZ205, which was something in between. This is M51. This is clearly not the same as that. So what did Bade say? He didn't say really anything about interpretation. He just compared with the disk and with globular clusters. And so if you look at the globular cluster, this is a globular cluster of our galaxy. Well, you might say for yourself whether the stars in there look like the stars in M32. The advantage at that time was that for globular clusters, people could take color magnitude diagrams and basically study the populations in that way. They also then looked, so the globular clusters were situated in, well, as you know, around the bulge of our galaxy. You can also take an open cluster. In that time, that picture doesn't look very good, but it contains some bluish stars. And there, the difference basically is that here, there is a main sequence which goes much farther down to higher temperatures than here. And clearly, it's later, people have realized that this is because there are younger stars present, and these are still on the main sequence, while all the other stars have moved off the main sequence. So there's a few things with this population picture. So population 1, population 2. People nowadays, I think, in this room have not heard the word population 1, population 2 at all anymore. I think in the beginning of John Carmody's career, that word was used a lot. And now it hasn't been used. Why? Because it has also led to strong confusion. Because what did we see in NGT 891? 891, we looked at the thick disk, and the population in the thick disk there looked like the population of M32. Later it shows that the population of M32 are fairly metal rich, while in the thick disk here and also in the halo the population are metal poor. So this whole idea of population metal poor, metal rich is not encompassed in population 2. So population 2 contains both the metal rich and the metal poor. The bulge, for example, would be population 2 according to Bade. So I would not encourage you to use population 1 and population 2, or just say what it is. So, having done that, of course this stuff one has to have some tools to interpret it. And this is actually really old science already. I mean, this is not like the Hubble Deep Field, which is only from the beginning of the 90s. This is stuff from the 30s and onwards. So, as I'll show, that theory has come to some quite unambiguous results. It's crystallized out quite a bit. So, Hertzsprung-Russell diagram. Hertzsprung was a Leiden astronomer from the 30s. So, they discovered that there is quite a nice relation between color and luminosity, or theoretically spoken, between temperature of the star, effective temperature, and luminosity. So you can use various terminologies there. A star goes through several phases. I'm sure you all know these phases. The point is later, when you look at objects at redshift 4, whether you can distinguish, well, this is main sequence, this is there, this is there. That's, of course, not clearly, does not necessarily have to be the case. So, very important, main sequence at a certain turn-off. Star moves off, starts burning helium in the core. At some point, the helium is finished. It starts. Here starts. Here the hydrogen in the core is finished. It starts burning hydrogen in the shell. At some point here, then the helium in the core starts burning, and the star goes to the horizontal branch, and after the horizontal branch it starts doing all kinds of things. It starts going to an asymptotic giant branch with burning in two different shells. And then it does all kinds of things there which are not very well known. And the reason they're not that very well known is that they go very fast. And the time that a star spends, and the number of stars, for example, in a globular cluster, in a certain phase is inversely proportional to the time that the star spends there. So if a star in a phase like this spends 10,000 years, and the rest of the thing spends, spends 10 million years, there's a factor of 1,000 fewer stars there, even though they might be 1,000 times brighter. Good. So this is very important to know, to realize this. So the lifetimes of the stars in the phases, very important, it's usually a factor 10, main sequence, RGB, horizontal branch, extended AGB and so on. I guess these ones are not that well known, and they might also depend on certain things like the metallicity, like the mass loss, which is assumed in those models, and so on. But this is about a factor of 10. Then the fact, of course, is that RGB stars are in some bands more than a factor of 10 brighter, so they dominate. And then in some bands, well, this doesn't happen that often, but sometimes it is also, in blue bands, it can also dominate the RGB again, and so on. Yeah. I know, I'm sorry, I just started realizing this, so good, I will use the mouse. And if you like, you can go into all kinds of details about these populations. Good. So once the phases are there, also we should know that, you should realize that people have tried to calculate these things. I don't really know very well who started all this, but I do know that a lot of the codes nowadays that are being used are all descendants of the Kippenhahn code, which might be a bit dangerous, because if that code has certain assumptions which are not completely right, then most of the codes nowadays could have that in them. But these codes are being tested on clusters, especially so much that there is quite a bit of internal consistencies. What you see on this diagram is that the stars, that massive stars move much quicker, burn their material much quicker, and after a short while are gone. And that's why globular clusters, for example, do not have these massive stars anymore. If you go to the faint stars, like the sun and so on, it takes them billions of years to burn. From these tracks, say the tracks are the evolutionary trails on the diagram. People make isochrones, so times of constant age. So those are lines here. Those are all lines of stars along which the mass of the star varies, and they all have constant age. And you see that there's a few numbers written on the top here: Z, Y, and 2 Y's in fact here. Z is the metallicity, I'll come to it in a minute. Y is the helium fraction of the star, and as a result, the place of the tracks vary in some kind of systematic way. Here there's 2 sets of isochrones from 2 different groups. There's the Padova group of Marigo Girardi, and then there's the Teramo group of Salaris and Cassisi and so on. And they look very, very similar. So it's not, if you have to choose a set of isochrones and so on, it's not that you should choose certain ones because they're better than others. It is possible that some isochrones present more phases of evolution than others. I mean, this just depends on the people. Some people are more careful than others, and so the careful people stop at the end of the top, at the tip of the RGB. Less careful people, they also produce the results from their AGB calculations, and still other people also produce the later phases where the planetary nebulae come in and so on. You have to realize when you use that those phases, the computer can just give numbers, but they depend on certain things like a mass loss rate, which is unknown, and depend also on other things like opacities and treatment of convection and so on, which are all to a certain extent known, but there are very few options to really test that very well. And during I think my third talk, I'll go into this a bit more. So metallicity, this is, well, we are astronomers, so we use some strange notation here. X is the fraction hydrogen, Y is the mass fraction of helium, Z is the mass fraction of all the rest. So also things like oxygen, carbon and so on are also metals. Then we use Fe over H between square brackets, which is the Fe over H, so the amount of, officially the amount of iron compared to hydrogen, compared to this amount of iron, mass fraction of iron over hydrogen of the sun. There should be a sun sign in the log, and in that case this is traditionally people have used for metallicity, they used Fe. In recent years this has changed and people then use mainly use Z, and they use for Z, well, this number also has gone up. Before it was 0.017 and now it's 0.02. So if you really want to be exactly sure what is being used, you have to go to the paper or to the reference or whatever. But there are slight differences. And of course the fact that there was some adjustment a few years ago shows that people don't know this number also that well. Initial mass function, if Daniela was thinking that I would spend a lot of time on it, she's mistaken, but I will spend a little bit of time on it. Only now the initial mass function is needed to calculate, well, if you take a color magnitude diagram, you can see how many stars there are as a function of mass, so you can basically measure the mass function at a certain time. You don't have to run this back to time 0 to get an initial mass function. There are lots of mass functions that have been used in the past. For example, there are so many of them because numbers at high masses are difficult, because there's few high mass stars available, that things do vary sometimes from cluster to cluster, also because of statistical effects, that if there's so few stars, some clusters have more than others just because of statistical noise. At the lower end, it's now quite well established that there has to be some turn-off. Realize that if you don't have a turn-off, that the amount of mass goes up quite considerably. So you can have a factor of 2 extra if you have a salpeter mass function compared to, for example, a Krupa mass function. So this you also have to realize when calculating stellar mass to light ratios. So, good. So once you then have calculated your stellar model, and you have calculated stellar model for a whole grid, and then you want to you want to fit it to the data. But out of your model, what comes out of the model are temperatures and luminosities, and these luminosities are integrated luminosities. And you need to compare that with observations, and observations have things like colors and things like luminosities in a certain band and so on. So you need to have some you need to get a conversion between a color and a temperature, and you need to have a conversion between a magnitude and the full luminosity of the star, and this is a so-called bolometric correction. The Padua codes nowadays do this by itself, so they calculate colors for you because they have some kind of recipe. On the other hand, the relation between a temperature and a color depends very much on the spectrum you're talking about. So this is actually it is a very difficult job to really do it well. Not for B minus V because there are lots of data, but imagine that determining the transformation between a temperature and color for a globular cluster where the metallicity is low is different for a solar type star where the metallicity is solar. And if you have globular clusters, maybe you can use stars to see what really the relation should be. But if you have, for example, you're talking about bulge stars or whatever, there is no stars that you can use to do this, because those bulge stars that you use usually are full of, well, sit in the bulge and have a lot of extinction in front of them, and so it makes it very difficult. So this is not a trivial step. So, but people, of course, they can shift, and as a result, they can then, if they do this on a number of observations, they think, well, this object has to be close to that one and so on. They can independently derive also information on that. So this is a very impressive result. I can show you an example of a globular cluster. Work by Harvey Richer. So here is a color magnitude diagram with HST, deep HST, 120 orbits. So you can also see it from the, oh yeah, sure, I should do it with the mouse. You can also see it from this diagram. The data go to magnitude here, magnitude 28 here. That is deep. And unlike most of the HST color magnitude diagrams, there's almost no scatter here. There's almost no clouds of points. So have they cheated? No, they have used proper motions to say which of these objects are member of the cluster and which are not. So because of using the proper motions, you can weed out the noise or the noise quite well. So here on this you can see the different phases. You can see the main sequence here, the turn-off here, actually quite small amplitude here. There's a red giant branch, very few stars on the horizontal branch there. And then what you do see here in this diagram is lots of white dwarfs. And white dwarfs are then the end products after the planetary nebulae phase and so on. And this work in fact went about the white dwarfs and what kind of velocities they get when they go the late phases, and whether they get an effect. Yeah. The message from this picture is that you can get very accurate color magnitude relations, that they can be fitted almost completely well with the current day theory. These are other clusters, and all these clusters have a different color magnitude relations depending on their age, depending on which you see from the turn-off, and so on and so on. Good. How do you determine the age of a cluster? That is not so trivial, because the age basically depends on the place. It's very much a function on the place where where the turn-off happens. So where the sequence goes away from here. So people use in practice, they use a couple of measures. One is the distance between here, the bluest point, and the position of the horizontal branch. This is also well calibrated in principle. One is the other is a horizontal place between here and the position of the beginning of the RGB. So these are, although not theoretically important, but these are ways for an observer to get a quantity that can easily be correlated with age. Or you can do something more sophisticated. But this is something that I guess some people in the audience are working with nowadays. This is from the IEC group of Aparicio and Gaillard. So they have some software, IEC Pop, IEC Star, that allows people to fit multiple populations from stellar evolution calculations to real data. And I'm curious to start looking into it and how this works. Well, now let's apply the theory to some data in the local group. The local group has the advantage that you can go quite deep and measure, as you saw. I mean, the stars are visible, easily visible, and measure the star formation history basically to form color magnitude diagrams. So this is the kind of data that people are getting nowadays from ACS, from HST. realize that this is still all HST from 20 years ago. So there is, maybe this will get better, but things like JWST will not work in the optical here, they will work in the infrared. So I wonder whether people will have to do all their theory on the basis of infrared, where there is no theory available yet. Or not much. So an example is the Tucane dwarf, Tucane here. It actually is not, there are much fainter ones, of course. Where you see from the diagram that it's mainly all old with a large horizontal branch, blue horizontal branch, because the metallicity is very low. I don't know what to think about this one, but this probably is a younger component which is also which contains a fraction of the stars. So this is that's the information that you get from here. Take another one, Draco. You get more or less the same picture. So you get this old population. Here you have a little bit of main sequence probably, which gives you this peak here at a younger age. Now let's go to something a bit more difficult. M32, we've seen it. M32 looks reddish. Well, what does it look like? It looks like this. So it looks, if you look at this and then you want to tell me, well, what's the first thing what's the first thing which comes up in your mind? It's white. It's really white. So the color magnitude diagram is very white, which indicates a range, a considerable range in metallicity. Metallicity is the parameter that changes when you go from here to here on it. Also, there is apparently this can be fitted with a range of ages. I'm not saying this is the only solution. Age and metallicity, as I will show later, are very degenerate. So this is a solution, and there might be a solution. You can minimize, for example, for the age range, and then you get then you get more metallicity range, and so on. NGC 147 is a fourth dwarf elliptical near Andromeda. You see that here the giant bunch is thinner, and you get a smaller range in age. Or clearly here the fact this is horizontal branch. This is not age. So the discrepancy cannot be solved. Now let's go to some other ones. This object is blue, and then of course you see it also in the HR diagram. You see, or the color magnitude diagram, you see a huge main sequence, which then leads to a lot of very young stars in this object. And this is what you expect. Also, what they find here is a lot of very old stars. What is unique about this, I wouldn't be able to say. Whether this fraction of old stars is so very constrained is not clear to me. And last, the SMC. In this case, SMC has a lot fewer giants here, and it has a large main sequence, so it has this kind of star formation history. So this is what we can get for galaxies in the local group. So, yeah.
Can I ask a question?
Of course, yeah.
So we have these age solutions.
Yeah.
And then also calculate that back to a model density field or something, and that you can get residuals from that colorectal model.
You mean, what do you mean with model density? I'm taking the galaxy as a point. So you think about resolving the galaxy?
I think about transforming those ages
into
ice growth.
Yeah.
And subtract those from.
That's the way the model works, more or less. The model works that way, and it works until what's left is. I haven't worked. I mean, I don't know whether people in this room have worked with the package and can answer that question. I personally do not think that the solution is, because usually in papers like that there is not, unless you have a very thin RGB, there is no discussion about uniqueness. Anyway, dwarf irregulars. All dwarf irregulars have an old population. It looks as if you have continuous star formation here. And what I didn't say is that different regions in the galaxy can have different star formation histories. For NG 205, the region that I showed was the center. That center contained a young as an old population. If you would have gone farther out, but there's no ACS data for there, the population is again completely old. So, now, okay, this is the easy stuff. Now, of course, we're going to go further out, and the rest of the rest of the lectures are going to be about objects that are further out. This is San A. San A looks very much like M32. So it has a very, well, you don't go to the main sequence turn-off. Therefore, that San A is too far away. It's 4 megaparsecs. What we do see is that the main sequence of the giant branch is very wide, so there's a considerable metallicity spread in the object. And this is the case, in fact, for all galaxies for which we have been able to do that, but there's not many of them. Another thing is blue stragglers. So let's realize that stellar evolution codes that we are employing do not contain blue stragglers, and they do fit. So you can fit an elliptical with a model without blue stragglers. So what does it mean? That in the data of the elliptical, the blue stragglers are not important. It doesn't mean that the blue stragglers are not there. I'll come with an example. But it shows that in the red, where we usually have data for the elliptical, the blue stragglers are not present. I was first thinking this is impossible, because blue stragglers are basically objects, are binaries, where one of the stars has been rejuvenated by gas from the other one. So then it can sit on the main sequence, or pretend it's a main sequence star for a bit longer. And if you assume that two-thirds of the stars are binary, you would expect there to be more stragglers. But this is of course not true, because of the two-thirds of the stars that's binary, lots of them, only a small fraction is contact binary. So that material from the one can go to the other one. Anyway, there are objects that have blue stars, have blue stragglers, and they're clearly there. And so it'll come back in a minute. Another thing is that what people don't understand is the horizontal branch morphology. So it is the case that if the metallicity is low, you tend to have often a horizontal branch which is very much to the blue, and cuts the main sequence in often in that area. But there are clusters like this one which have the same metallicity, which does not contain a blue horizontal branch. It contains a so-called red horizontal branch. So it's not clear, it's still an unsolved problem, why some clusters have a red horizontal branch and some clusters have a blue horizontal branch. There are attempts I've seen to see in integrated light whether you can see the effect of a blue horizontal and a red horizontal branch, and it's maybe possible to also to do this. But it's something in stellar evolution theory that's not very well known. It might have to do with the helium abundance, it might have to do with something else. This is now, but the field is not boring, not at all, because recently people start finding in clusters, globular clusters, Omega Cen is like a galaxy, also globular clusters. They start finding features which, well, what is this? It looks as if there's two main sequences here. So, in fact, when you hear this, the bottom falls under your way, because a globular cluster is something that is really that is supposed to be the thing that is used for calibration of stellar evolution models and so on. If that then happens to have two main sequences, that's very strange. But it's not so bad. What does it mean? That you just have an event which creates the cluster, and then there's some self-enrichment later, which then some gas which is left, which makes another generation of stars, and that generation has very similar properties. So it's in fact, it's in principle possible. but people are finding in detail, they're finding lots more of these things. There's also finding double turn-offs and so on. So this field is definitely not dead. So those are a couple of things that are not understood. And this, and I like to finish this bit on resolved stellar populations about the future of resolved stellar populations. So this is a picture where it says how far we can go with telescopes as they go bigger. Oops, yeah. So if we are now at an 8 meter, this is an 8 meter, we reach a point source sensitivity where we at a reasonable signal to noise of about 28 or so. This is what I showed on the. This is for HST also the case, but it's also for more or less for on the ground for the VLT. If you then go to a bigger telescope like the EELT or something like that, you can go to this place, which is about magnitude 31. That means that you can go, say, magnitude 3 or 4 deeper. But where do you really want to go to separate age and metallicity is to go to the main sequence turn-off. So these lines are there for Virgo. So the main sequence in Virgo is magnitude 35. So you'll not be able to go to the main sequence in Virgo. You'll be able to go to a little bit better than the horizontal branch in Virgo. So with the EELT, we'll be able to go to do the kind of pictures that I showed for old populations to Virgo. But the pictures that I did for M51 and so on, of course, we are there already now. So there's going to be some increase, some improvement. It's not going to be dramatic. That's all I'm saying. So, to summary of resolved stellar populations, stellar evolution stellar population modeling is purely based, is of course based on stellar evolution codes. And all of stellar evolution codes are based on clusters, globular clusters, open clusters. Without them, we would have been completely lost. Galaxies that can be resolved in stars can show a wide range of star formation histories. And although many things are understood, there are a couple of things like, IMF I didn't talk about, but there are still lots of things that are not understood. Second parameter problem, these double main sequences and so on are not that well understood. So we need to, this bit on resolved population has to be done to go to the next bit, which is the unresolved subpopulation, because unresolved is just a poor man's version of resolved. But we can't. We have to work with it. Why? I mean, it is rather stupid when you hear colleagues that tell you that you cannot do anything, and this has happened to me. That say, well, you're working on unresolved populations. I don't believe any of it because you don't see what you're doing. Well, maybe that remark by itself is correct. On the other hand, there is no alternative. So most galaxies in the universe are so far away that they cannot be resolved into stars. So we need to think about ways of resolving them, ways of resolving them using the spectra. And the spectra, of course, has lots of pixels, so there we can do things. So galaxy evolution with redshift can only be done using unresolved galaxies. And then I put a statement here, is it easier to average the stellar properties with unresolved populations than with unresolved ones? If you look at a globular cluster and you want to get a spectrum of that globular cluster, I want to compare my globular cluster, a spectrum of my globular cluster with a spectrum of a globular cluster at M87 or so. Then it's really difficult to get that spectrum for a nearby globular cluster. This, of course, is not a serious statement here, but you have to take into account. When you do comparisons, you have to compare like with like, and not one star in a globular cluster locally with a lot of stars farther away. So, what can we measure? well, lots of things. In broadband colors, in UV, near IR, optical, it's going far away. I mean, and then of course, I'm here giving a talk about stellar populations. Because this light is coming from stars, I'm constrained to these three regimes basically. Because stars are hot, photospheres of stars are fairly hot, so the amount of radiation in the radio and so on is very limited. And anyway, this is not the scope of the talk. Spectra, 0D, 1D, 2D, surface brightness fluctuations. It's also interesting. So how bright is a galaxy, and what's the surface brightness, and how quickly does this vary? In fact, it's something in between resolved and unresolved populations, because you don't really resolve the stars, but you still see the remains of what was there, and what you could have seen if you had been closer to it. And then, of course, there's lots of indirect indicators, like, for example, what Daniela was talking about, Spitzer emission of dust which is heated by stars, and gas which is radiating because it's heated by stars, and so on and so on. So we have to then somehow address the problem. You have seen that the star formation histories can be, and probably are, complex. So, but on the other hand, complex, if you want to address some complex problem, you still have to dissect it into smaller bits. So we're going to work through, and this is what is being done, through the single stellar populations. A single population is a population with a single age and a single metallicity. So this is all the stars, in fact, which are found along an isochron. For that, you have to assume an initial mass function, or derive it. And it's useful to fit simple stellar systems, such as globular clusters and elliptical galaxies. Of course, I don't really mean simple, but it is the first thing that you can try. And then later, you can then go as a second step, trying to get the complex star formation history of it. So, this figure is, I guess, some people have seen this already before. So what am I talking about? Talking about evolutionary population synthesis. So this is the population synthesis using stellar evolution theory. And what you do, this is based around an isochron, evolutionary tracks or an isochron, which is then converted to the observational plane, as I said before, using color temperature conversions, color conversion, and so on. And so you have along the isochron all kinds of stars, which then along the isochron have a distribution in temperature and gravity. You integrate it, and you get some output. And the output, here I'm talking about colors especially, but in principle this can also be applied to spectra and so on. I'll come back to it for spectra. But you get an output set of colors, which you then compare to a set of observed data, and then you can go back, or you change your metallicity and your age of your isochron, and you see whether this makes any sense. So this is in fact very simple. The difficult things are to find the right color, effective temperature comparison, and so on. The fact that it is difficult is just shown by the fact that infrared colors, J minus K and so on, from one model to another, still vary considerably by up to a tenth of a magnitude. So, when you talk, first I'm going to talk about colors. So, when you see colors, you have to realize where the light in a population comes from. So this is a population from this paper. This is from Ariston. This is from solar metallicity, and here is the V band, and here's the K band. People who have looked at a picture of a galaxy in V band and K band see a big difference. In K, the graininess is much larger. And why? It's because the giants are much more important in K. And this is obvious because the giants are redder. But it's so obvious. Just go and this evening or so, when you have nothing to do, go and do what I did. So go to the Hubble archive and go to take some look at some whiz-pick pictures of an object and take it in for example H, and then also do the same with an object in V and look how the galaxy with the same telescope, what the difference is. So the main sequence is for younger ages is fully dominating. Well, this is normal. This is also from the star formation histories. And for the older populations in V-band, main sequence, so this is mainly the area around the main sequence turn-off, and the giant branch are competing, so they have more or less the same contribution. Then there's some other phases, the horizontal branch, which is always a reasonable fraction of stars, but never dominating. And then you have the AGB, which in the V-band goes to something like 20%. All of this, of course, is according to current theory. This is not observations. When you then look at the K-band, it's a very different picture. You see that in K-band, the main sequence is really never dominating. That is quite strange. So dominating in K-band is the AGB for the phase in which the AGB is important. This is around 10 to the 9th years. And later, the red giant branch. So these two show fully dominate these bands. So if, for example, there is a large contribution of stars, of AGB stars, the V and the K pictures should really be different. This picture is very important. You should all know this by heart, because this is, when you work in populations, this kind of, it's all in the back, you always have to have this in the back of your head. So, these are the simplifications that I was telling you. Then realize the following, what we saw in that picture was light. So that was luminosity. It is not mass. So, in the previous picture, we saw that in K-band, the light is dominated by RGB and AGB. The mass is never dominated by RGB and AGB. The mass is always dominated by the main sequence. Right, now we start talking about something nasty. This is the age metallicity degeneracy. So from these pictures, and you know of course already, is you can, so when a population gets older, what happens? Stars from the main sequence, they move to the RGB, so the population becomes redder. And in fact also becomes fainter. Then I made a mistake by saying that this happens to individual stars like the Sun also, but the Sun gets brighter in fact this time. This is a side remark. For metallicity, so if you go to larger metallicities, the opacities of the stars increase. So and the opacity is especially to be found in the blue. So this is where the lines are. So the stars that way become redder, because the blue light gets eaten away. So since this behavior of age and metallicity is similar in a way, you can, if you then just have colors, you can replace the, you can compensate for an effect of metallicity by an inverse effect in age. So that's nasty, because that way if you have just a certain color, so you cannot really derive age and metallicity at the same time. So the same, later I will talk about line strength. This is basically the same for lots of different line strength, and that's color as well. Let's see. Okay, so what I was saying here is that in the diagram, basically, if you have as a function of age, these are some composite models. So for solar metallicity, 2 times solar and so on. So you measure, for example, B minus V equals 0.9. Now this can be that you are here at 3 gigayears and twice solar, or you are here at 8 gigayears and solar, or you are here. Good. Well, then you say, well, yeah, but this color is not right. I use a different color. R minus I. Same thing. Doesn't help. You can do any color you like. Doesn't help. So then if you do this, you put these two diagrams together and you plot them in a color diagram, then what happens is that the theoretical tracks fall on top of each other. And so if you are sitting there, and you have to sit there because here you can't be according to the models, then you don't know where you are, on which of the metallicity or age lines you are. Well, this is nasty, but there are ways, of course there are ways out. So we go to the infrared. In the infrared, the light is much less affected by age than metallicity. So it's a different way. So you see that in this B minus V again, sorry, J minus K, this line doesn't reach, so it doesn't reach this line here. So it's already a little bit better. And the diagram showing the color diagram shows at least that the lines of constant age and lines of constant metallicity start diverging a bit. But here, you see, this diagram is not really good because you still have only a range of 0.05 magnitude, so it's not very fantastic. But it can be done, in principle. So going to the infrared, you can, in principle, this thing of resolve age and metallicity at the same time. And this has been done. This is, and you see, this is an elliptical with lots of globular clusters around it. And people have measured the colors of the clusters in an optical infrared color, very wide baseline, and an optical color. And this is the grid, this line, this line, and this line here. And you see indeed that the lines of different, let's have a look, the lines of different age are perpendicular, are at least somewhat different from the lines of different metallicities. Whether this is ideal is, I think, is not the case, because the error bars in the points are probably, well, they're probably not larger than not larger than they should be, and it's very hard to then say based on such a point, well, this has to be 3 gig years or whatever. But in principle, it's possible. The other problem, big problem, with the infrared colors is that a lot of the light in the infrared, as I showed before, depends, if you are around 1 gigayears, depends on AGB stars. And AGB star evolution is very badly constrained, because just the fact that there are so few stars, so few of these stars available. So that means that some of these models show a dip around here as a function of age and so on. This is not in all models. And so then the models, the line that I used, and those models, then in such a case, a model is crucial. And if that's not certain, then the ages that come out are also not that certain. So you can then say, okay, well, infrared we've done. It works, but not very well. Go to UV. But then let's go to the speaker of the previous talk. I mean, the UV is not very nice because the extinction is very large. So in principle, you can, here, there's a number of colors here. These are models. I need to have some lesson in. So here, this is 2.2 is a narrowband color around 2200 angstroms, 2500 angstroms, 3000 angstroms. So you see that the lines of constant age and the lines of constant metallicity have a different slope. So in principle, it's possible to separate age and metallicity that way. But this is actually really interesting to see. This is M67. Here there's two pictures. One picture is the cluster in the optical, and one is the cluster in the UV. So this was, I think, with the HUT or so. You see that one of the stars, this star, is extremely bright in the UV. So it consists of 90% of the light. Well, of course, when that happens, then the stochastical errors are so big that a diagram like before doesn't really help at all. So that means that the UV already from this point of view is really hard. The second thing is extinction, and I don't know whether I have time for that. I'll look at the chairman. Can I still do the extinction bit? It takes about how many? 5. Well, Let's try. 10 if you want. Let's try. You're probably all very tired. So, extinction. Because extinction is going to be, is already said, extinction UV is terrible. But extinction, to work with colors, extinction is also terrible. I mean, it's really, it has caused a lot of trouble in my career, and it's probably caused a lot of trouble in the career of most people. This picture shows that this spiral, which is seen in front of an elliptical, this is a fantastic picture, has extinction out here, really far away from the center. So, I mean, the point with extinction is you really don't see it. Oh, that's but it does affect your data. So, okay, well, here, this is an extinction curve. There are variations in different environments, depending on metallicity and so on, but out here, so this is 1 over lambda. Huh? So here you're talking about, this is the beginning of the optical, so out there it's not that different. So you see that the extinction at 3000 angstroms, well, call it U or UV or so, over AV is a factor 2, and then it goes, well, to very low values. And this is the very UV, and of course extinction in the around Lyman alpha and so on is amazingly high. Well, this is Sombrero galaxy in, I think something, well, it's a composite of optical colors, and this is K-band, and you see that the galaxy looks very different, but you see that the extinction there is in K-band indeed is very little, and it's something like AK, the extinction in magnitude is about 1/10 of the A in V. So this is more or less, well, let's say it's a very simple formula. Extinction is an attenuation, is an E power. So for a star, the nice picture is you have a star and you have extinction in front of it, and so a certain fraction of the light of that star is removed, and whether it's in if A lambda over AV is a factor 2, you always have that a factor e to the power 2 more light is being removed in the other band, in one band and the other band. Very nice. So this is correctable. This is what people did in our galaxy. This also works if a galaxy sits behind a screen of dust. And a screen of dust, for example, is our own galaxy. There's galactic extinction, which sits in our galaxy, and this works as a kind of screen in front of a galaxy. And well, we can correct for galactic extinction very well. We do it by assuming that the amount of H1, well, this was in the past, but anyway, the amount of H1 or the amount of dust is very proportional to the amount of extinction. That seems to work pretty well because everyone seems to use Schlegel et al., or there's probably some later papers based on Sloan which are replacing this now. So that's all fine. Now the difficult part starts. So the sombrero, this is a paper that I did with the chairman of today, well, not the chairman, but the other organizer of the conference in 1991 even, where we see the extinction of the sombrero on the minor, and you basically measure it by assuming symmetry. So you say, okay, this side has to be the same as that side, and then you can see what the extinction is. And you see it's a large amount in V up to 2 magnitudes, and it goes there. And more or less this is scalable. So this is more or less scalable. Because you can think of this thing there in the sombrero as a screen, because it's like a ring in front of the bulge where most of the light comes from. But if it doesn't, not anymore, this is what it really looks like. This is what dust really looks like. It doesn't work if you want to measure the extinction in this, the amount of extinction in this galaxy. This is NGC 891 like before again. How are you going to do it? Are you going to use a screen model for it? It doesn't work. The extinction sits between the stars. So there is a star, there is a cloud, there is a star. There is another cloud, there is a star. Some bands, so you basically observe the light up to optical thick in a certain band, and up to the moment that there is so much dust that it's optically thick. So this happens earlier in B, then in V, and so on. So you look at up to a certain radius in each band. And so the information is basically not there anymore after a while, after a certain while. This is, everyone who works on galaxies should have seen this picture. So this is a zoom in on the previous picture. This is an HST. So there is a lot of dust in this galaxy, and this goes above. It goes quite high above the plane as well. So you can measure the extinction if, in rare cases, if you use symmetry. If you use galaxy with extinction in front of others, like the previous picture we saw. If you compare it with a color that it has to have, so if you assume, for example, well, 2 minutes. If you compare it with, if you say, well, the color of a galaxy always has to be B minus V equals 0.8 or so. And then, of course, when you measure something, you can then correct for it. But that's really not easy, because you have to correct based from a different band. In that band, the light has to be from the same objects. And in, for example, 891, you can't think that, for example, in the K band, the light is the same, comes from the same stars as in the V band. You can use, people are reduced usually to go to statistical methods, and that's not very pleasant. So measuring extinction in general is very hard. And here I show a picture from Ron Buta's recent preprint, where the galaxy is shown in 3.6 microns without any extinction, and in this shouldn't be a 9, this should be a G. So this is a blue band. This is a blue band, and you see indeed that there is a lot of extinction in the G band. However, for classification purpose and so on, the effect is much less than people often state. People publish Nature letters and so on. Well, the type of the galaxy, of this galaxy in infrared suddenly has changed by 2 numbers or whatever. That is only happening in a few particular cases, but in general, it's not really the case. So, just to come back to that picture as my last slide, if you include extinction here, you move quite a bit. So, to determine really metallicity, it's better assume there's no extinction. Thank you very much.
Hi, Reynier. I had 2 questions regarding the part of the resolved stellar populations. I noticed in the Hubble pictures you've shown that the low brightness stars tend to fade out rather quickly. Saw a couple of galaxies in which you could only see the main turn-off. Now, I was wondering, in what way is it important that you are missing those to estimate your initial mass function? Can you just estimate that based on everything beyond that, or do you actually need the low luminosity stars for that as well?
I am not a specialist on measuring the IMF, but it's in galaxies like the ones in the local group M33, M31, and so on. You don't see main sequence stars. You see all the stars you see there are red giant bench stars, are giant bench stars and horizontal bench stars. So the range in mass there is very small. So I think this is probably not enough to really measure the IMF. I mean, is that correct, Daniela? Or yeah. Oh, that's okay. Something else. Yeah.
All right, and the second question I had, it's more stellar evolution related question. I noticed that in the lowest parts of the color magnitude diagrams, the scatter seemed to increase dramatically on the main sequence. Is that just a data noise point? All right.
Yeah, because you saw in the picture where you have proper motions, it goes away.
All right, thanks.
Hi. Well, first of all, just to say that the result that just showed before, obtained with EFEPOP, are unique.
In what sense?
In the sense that you obtain only one possible solution, not both or 2 or 3 solutions. I don't know if
that's a very political answer, because unique, you mean it all has error bars and so on, and I guess if you don't have a turn-off, there cannot be any unicity.
Yes, but
up to where you go.
Yes, but you need to go, I think, 1 or 2 magnitudes below the turn-off to have this unit.
Okay,
now I have one question, and it's about the second parameter. Can this second parameter change the obtained star formation history? Because if it can, for example, modify the structure in the horizontal band, for example, can change the color in the turn-off point?
I think they're independent, no? So, you mean change means that what the program says is that what comes out of the program, or? I'm not sure that I don't think that I don't know whether the turn-off point has anything to do with the second parameter problem.
Yes, that was I was asking for.
I don't know whether someone else knows and try to find out.
How much do we know about the ages of the oldest stars in the interarm regions of M33?
I think it's not so much. You can't go to the main sequence turn-off. So I'm not so sure that you can resolve the age metallicity degeneracy there. I mean, I don't think you can really prove it's more than 3 years or so. No.
Okay.
No more questions? I guess we're all tired. Let me make one small announcement before we thank Reynier. We have a special welcome dinner tonight. It's going to take place at 8 o'clock. At the -1 level in the room, in another room that is opposite to the usual restaurant where you have breakfast and lunch, okay? 8 o'clock tonight. And, yeah, I think that's basically the message I wanted to give you through. So let's thank Reynier and thank all the speakers today for